Hello. So in the previous video, we progressed in our discussion of thinking through differentiation from first principles, and we got all the way to the point of understanding that the gradient at point B here, the gradient of the tangent line at point B on the curve y equals x squared is 6, right? We saw that it's tending towards 6. Now, this is a great result, and we just essentially worked to this point, this overall general calculation by just beginning with the study, or revising, or quickly reviewing our study of how to find the slope, the gradient of just a normal straight line with constant acceleration or constant increase. And now in this video, we're going to expand a little bit on all of this in a general way. We're going to generalize this calculation with what we've found. This is where things really get fun, and I think maths comes to life when we start thinking more generally and a little bit more abstractly. But in any case, in this series of videos so far, we've basically just gone from incremental step to incremental step, similar to how when I first taught myself calculus, or in this case differentiation is what we're discussing in particular. And so what we want to do in this video is we want to generalize the finding that we made in the second video. And so to do that, I want to re-sketch this graph here, this graph y equals x squared, the one where we found the gradient of the tangent line at the point B. And so I'm just going to draw the coordinate axes here very quickly. And we know that this is y equals x squared. The curve looks something like that. I'm just writing here y equals x squared to make that explicit. We've got our point B, somewhat of an arbitrary point at the outset, but we eventually defined it, and we've got our q sub 1, say here. Okay, except now we're not going to call this point. Well, we can call it B. Let's just call it B. Okay, and yeah, we'll call this. Let's just say q sub 1 again. Just for continuity purposes throughout all three videos, we'll call this q sub 1. But what we're going to say now is that B is no longer 3 and 9, right? The x coordinate is no longer 3, and the y value is no longer, the corresponding y value is no longer 9. We're going to just say, we're going to think generally, speak generally, we're going to say that it is xy, okay? And likewise for q sub 1, we're going to do the very same. But first, what we want to do is sort of take the exact same steps that we took in the last video when making this graph. We want to drop an altitude down from q sub 1. And we've got a horizontal line here from B to our points, which we can denote as C again if we would like. Call it anything we want, really. So we'll say C. And of course, this horizontal, the y value of C is going to be the same as B, because this is horizontal right across like this, just as the example in the last video. Now, what is this here? Well, we can denote that as delta y, and likewise this is delta x. Okay, and more interestingly, I suppose, is that if this, so in the last video we said, okay, we'll just say this is not 0.1, right? BC is not 0.1. Well, in this video we're saying BC, we're generalizing, we're saying BC is delta x. Well, from that point we can then start working on what are the coordinates of q sub 1. Well, if BC is delta x, we're going to follow the same logic as in the past video in finding coordinates of q sub 1, except it's a generalized result. We're generalizing here. And so q is going, the x coordinates of q is going to be x plus delta x, and the y value is going to be y plus delta y. Okay, and to summarize, I suppose, if the x coordinates of our q sub 1, our point q sub 1, is x plus delta x, where delta x, we know delta x is used to denote a small change in x, a very incremental small change in x. The corresponding change of y is going to be written as delta y. right? And this is, again, we're just expanding on basic knowledge that we already begins to crystallize in when we study linear, just straight lines, right? With constant increase or acceleration or whatever. And so the coordinates of Q are going to be x plus delta x, y plus delta y. Now, we are considering the graph y equals x squared. And we know that y plus delta y then, just like in this case where it was 3.1 squared, well, in this case, y delta y is going to be x plus delta x squared, right? X plus delta x squared. X plus delta x squared. It's the x value squared, right? So we're dealing with the graph y equals x squared. So we're just expanding. This is the exact same logic we followed in the last video, except we're just speaking more generally. And so in prefacing and making all of those comments to preface what follows, let's carry on now. We can write that, well, as I just explained, y plus delta y equals x plus delta x squared, right? And, well, what can we do now? We can expand this x plus delta x squared. What does that get us? That gets us x squared plus 2x delta x, 2x delta x plus delta x, and we can square that, so I'll put it in brackets. And from here, but we know again that y equals x squared, right? And so we can sort of continue by saying, well, delta y equals 2x times delta x plus delta x squared. And now we can sort of continue forward, where the gradient of BQ is going to be delta y over delta x, right? Which is going to equal 2x delta x plus delta x squared over all of that's going to be over delta x. Now, I suppose here's the important step in this generalization, because what we can now do is just simplify this a little bit more, right? We can factor out delta x, basically, is what we're going to do, because we've got a common term here at the top. So if I scroll down a little bit, I don't want to scroll down too much to get this, so the graph comes out to focus, so one can sort of look at and see and think about how all of this relates to the graph above here. But we can simplify this. We can essentially factor out a delta x, right? It's a common factor here in the top in the numerator. So we can just write this. I'll just write equals. Well, what happens when we factor out a delta x? Well, we get delta x times 2x plus, well, delta x. And all of that, again, is still going to be over delta x. Delta x, right? And we can simplify, right? Because delta x is going to cancel out here, and actually quite conveniently, in fact. And so they cancel like this and like this, or sorry, going to cancel like this. And so what we end up with is just 2x plus delta x as our result. Now this is really interesting. It's a very interesting result. As we let delta x become 0, or let's just say as we let it become 0, we're just left with 2x, right? If delta x were if delta x were to become 0, it's just 2x plus 0, so all we're left with is 2x. And why that's really curious is that because this is the formula for the gradient of the tangent at Q, at our point Q, right here, at our point, or at our point B, I should say. And it may not look like it because it's written very generally, but this is the formula for the gradient. This is our gradient formula, you could call it, our gradient equation, you could even say, right? Or maybe better to say gradient formula for the point at B. In other words, we have a very, very concise way of expressing the fact that we are letting delta x approach 0. We want this term here, in this expression, this term here, delta x, we want it to approach 0, right? And so we can write that in the following way. We can write the gradients, and maybe actually I'll write it down here. I have a little bit more space. We can write it here, equals, this equals, I'll make an arrow like this, this equals gradient, the gradient of the tangent at our point B, gradient of the tangent, okay, which equals the limit of delta y over delta x. So the limit of delta y over delta x as delta x tends to 0, which we just talked about, as delta x tends to 0, which is going to equal the limit as delta x tends to 0 of 2x plus delta x, which is going to equal, well, if the delta x tends to 0, right, let's just say it becomes 0, what is we left with? We're left with 2x. And there you go, we've got 2x. Now why is this so significant? Well, let's just think to ourselves for one moment. Note that when x has the value of 3, let's go back up to the previous graph here. Let's just remember this for 1 second, okay? We've got it down to the limit, delta x tends to 0 of 2x plus delta x equals 2x. Well, why is that so significant? Well, let's look at the previous graph from the second video, right? Because this graph here, what we've just done, the working here, is just a generalization of what we've done already previously in the second video. So, if at the point B, if the x coordinate is 3, well, what if we plug in that x value into the formula that we just derived? 2x. Well, 2 times, well, if x equals 3, 2 times 3 is 6. And what was the gradient of the point at B that we found in the second video, at the tangent line at B? Well, we found that it was tending to 6. And that is no coincidence. That is in no way a coincidence. Because what we're actually thinking about right now is differentiation, the very essence of the function of differential calculus, where when x has the value of 3, in this case, 2x has the value of 6. And so, the general result that we have right here in front of us agrees with the earlier result from video 2 when we calculated the gradient at the point B, where B was 3 and the x-coordinate of B was 3 and the y value was 9. And we can do this calculation, it turns out, for all curves, many curves, lots and lots and lots and lots of curves. And we can, instead of, in short, really, to conclude this video, I suppose, instead of writing all of this out every time, like all of the working every time, you know, for each point, for in each case where we need to find the gradients of the tangent at a point, we can just simplify by just using 2 symbols, or we have a special, or you could say a special symbol, which again is just the limit, where delta x tends to 0 for dy over dx. and we write this dy over dx because it refers to the derivative of y with respect to x. Hence, what could one say? We enter the wonderful world of differential calculus. All that this symbol means when one writes this, like when one's first taught calculus, they say, okay, what if you have xn? What is the derivative if y equals xn? And or let's make it in function notation, actually, which I prefer. So let's say f of x equals x to the power of n. Well, f prime, or sometimes people say f dash x, or f prime of x, is just going to be n x n minus 1, right? And you could write the f prime of x in this way. You could write it as the derivative, the first derivative, dy over dx, right? It means they mean the same thing, but what they're indicating, their definition, what they're indicating is all of this working up here. It's just, rather than doing all of this each time, we can just denote it by dy over dx.